Hello everyone, welcome to this 24th lecture in the NPTEL course on Riemannian geometry. So let me remind you of what we discussed in the previous lecture. So we introduced this notion of sectional curvature, uh, and one of the things we claimed was that sectional curvature in fact determined the Riemann curvature tensor, and in order to prove this we tried to abstract out this statement into a purely algebraic fact. So forget about the background geometry, but only think of the algebraic properties of the curvature tensor. So so to do that we considered a finite dimensional inner product space, and we looked at all the space of called RC of V, which are all the curvature like 0,4 tensors on V. So curvature like just meant that these tensors satisfied the symmetries that the usual curvature tensor satisfies, and it also satisfies an algebraic Bianchi type identity. Okay, and then the main proposition was that if we take a curvature like tensor and suppose this curvature like tensor vanishes on these sort of diagonal terms, then it vanishes completely, it vanishes identically. And the consequence of this was we did not prove this proposition. So the main aim of today's lecture is to first prove this proposition, but as a nice consequence of this is that if you look at the sectional curvature, which has this definition, and one of the things we proved was that the sectional curvature depends not just on x and y, but depends really on the plane spanned by x and y. So the sectional curvature at a point P is really a function on the Grassmannian, the set of two planes of the tangent space to R. Right. So a consequence of this proposition was that the sectional curvature completely determines Rn, right. So the main the first goal for today's lecture is to actually prove this proposition. I also explained last time that it's not completely surprising that that such a proposition exists, because we can take inspiration from instead of looking at 0,4 tensors, if you look at symmetric 0,2 tensors, namely symmetric bilinear forms, then one already has such a proposition, because for instance if you just look at the diagonal terms of the bilinear form, that gives you a quadratic form, and then there is a polarization identity that usually tells us that the quadratic form determines the symmetric bilinear form. Okay, so in any case as you will see in the proof of this proposition, we are going to calculate, we are going to I mean it is going to involve things that also appear in that look very similar to things that appear in the polarization identity for bilinear symmetric forms. Okay, so the proof proceeds in several steps. So the first claim is the following, that if you look at f of x, y, comma z, comma x, this is going to equal f of y, comma x, comma x, comma z, and both these quantities are going to be 0. So remember, my hypothesis is that f satisfies this condition, right. So if f satisfies this condition, then my first claim is that it satisfies these further two relations. So how do you prove this? Well, you calculate f on x comma y plus z comma y plus z comma x. This is 0 by hypothesis, but then using the multilinearity of f, you can decompose this into 4 terms. So the 4 terms look as follows, I mean the 4 terms are as follows. Now for the first and the last term, that's 0 by hypothesis, right, because these are sort of the diagonal terms which we are assuming are 0. So this is simply f of x y z x plus f of x z y x. Okay. Now the first term is obviously of interest, so that appears in what we have. For the second term, I use the symmetry in interchanging these two. So interchanging this with this, right? So that's going to be f of y comma x, x comma z. So that's the second term that shows up here. But by skew symmetry, I can exchange these two terms and I can exchange these two terms. Each one will incur a negative sign, but I am doing it twice, so I do not change the sign. So I just get twice f of x y z x, so which implies that f of x y z x is 0. Okay. But on the other hand, through the proof we already saw that this quantity f of y x x z by the symmetry of f is the same as f of x comma y comma z comma x, right. So that also is 0. So that proves the first claim. Okay. The second claim is the following: that f of x comma y comma z comma w is minus f of x comma z comma y comma w. So that means if you exchange these two, you get a negative sign, you incur a negative sign. So again, this is not true for general curvature like tensors, is only assuming that the hypothesis of our proposition that f of x comma y comma x is 0, right. Okay, so let us prove this claim. So by the first claim, if you consider a quantity of the form x comma y plus z comma y plus z comma w, that is 0. This is by the first claim. Now again I use multilinearity to expand this out. So this is f of x y y w plus f of x y z w plus f of x z y w plus f of x z z w. So again by the first claim, this term is 0, this term is 0. So you get 0 equals f of x y z w plus f of x z y w. But this is precisely what I am claiming here, right. Okay, so that proves the second claim. The third claim is that the terms that appear in the algebraic Bianchi are all 0, are all identically the same. So if you cycle through the first three, then under the hypothesis of the proposition you get the same value. Okay, what is the proof of this? Well, you take f of x y z w. Now by claim 2, I can exchange these two and incur a negative sign. So that is minus f of x z y w. But now by the skew symmetry in the first two entries, this is the same as this. Okay, so that proves this part of the claim. For the second part, you basically now exchange y and x. So again incur a negative sign, okay, and then again by skew symmetry, this is equal to f of y comma z comma x comma w, right. So that is exactly what I am claiming here. So this is also done. Okay, so now note that in the entire proof I have only used the symmetries of the tensor so far. Now I will use the algebraic Bianchi. So by the algebraic Bianchi, if you take f of x, y, z, w and cycle through the first three indices, then you get 0, but by claim 3 this is all of these terms are the same. So this is just 3 times f of x, y, z, w, right, which just means that f of x, y, z, w is 0, but this I mean these vectors were arbitrary. So this is for all these vectors, okay. So this implies that f itself is identically 0, okay. So that completes the proof of the proposition. Alright, so the next thing I want to talk about are in some sense traces of the curvature tensor. So the first thing is the Ricci tensor. So again the analogy one can give is with matrices. A matrix might be a very complicated object to study. So in linear algebra we do this trick of instead looking at the symmetric functions associated to the matrix. So in particular there are two very important symmetric functions, namely the trace and the determinant. The trace and the determinant have much nicer properties and they are basically real numbers, right. So they are easier to deal with. Similarly here we now have this very complicated object, namely the Riemann curvature tensor. We have already done one simplification. We looked at some sort of a diagonal and that defined the sectional curvature, and it turns out that the sectional curvature contains exactly as much information as the full Riemann curvature tensor by this proposition and its corollaries. But even so the sectional curvature sometimes is still too complicated an object to study. It is better than the full curvature tensor, but it is still quite complicated. So then we do what we learn in linear algebra, we take a further trace, and that basically defines the Ricci curvature. So here is the definition. So we define the Ricci curvature. So that is going to be a map that takes in two vector fields and spits out a smooth function. It is given by the following. So Ricci of x comma y at any point P is by definition the trace of the following linear operator. V goes to, so maybe let me write it in the next line so that right. So by definition this is simply the trace of the linear operator that takes a V to R of V comma xp acting on yp, okay. So where V is some tangent vector at P. So in other words let us define the following operator. So this is an operator from the tangent space at the point P to the tangent space at the point P. This takes the vector V to this vector obtained by applying the Riemann curvature endomorphism to V comma xp, and that is applied to yp. So then basically the Ricci curvature at P is simply defined to be the trace of this endomorphism. Okay. All right, so the main proposition is that this is a symmetric 0-2 tensor. Okay, so before I prove this, let me give you a little sort of linear algebra aside. This will be used to prove that the Ricci curvature is symmetric. So let V comma Q be, let us say, a finite dimensional inner product space. Okay, so given an endomorphism of the vector space, one can define its adjoint. So this is the adjoint is defined as follows. It is defined by the following relationship, that if you take the inner product of AU and V, so this is the same as the inner product of U and A star V. Okay, for all UV. So because the inner product is non-degenerate, this completely determines A star. Okay, and then the key fact from linear algebra is that if you take the trace of A, then that actually equals the trace of the adjoint. So for instance, for the standard inner product on Rn, we know that the adjoint is basically, given any endomorphism, you can write the corresponding matrix in the standard basis on Rn. Then we know that the adjoint is precisely the transpose, is the linear transformation corresponding to the transpose of the matrix, and then we know that the trace of the matrix is equal to the trace of its transpose, right. But that fact holds more generally for abstract inner product spaces. So that is the little linear algebra aside that we will need. So let us now prove the proposition. So, so the first step is to show that the Ricci tensor is the Ricci curvature that we have defined is actually a 0-2 tensor. So it is enough to show C infinity linearity. So it is enough to show that Ricci of fx comma y is f times Ricci of x comma y, and Ricci of x comma fy is equal to again f times Ricci of xy. Okay, so let us prove the first part. The proof of the second part is very similar. Okay, so let's focus at a point P in M. So let AP and BP be endomorphisms of the tangent space at that point. So here AP of V is simply given by R V comma XP acting on YP. Okay, and BP of V is given by RP of V F of P times XP acting on yp. But now we know that the curvature endomorphism itself is C infinity linear in all its entries. So in particular, when you restrict localize at a point P, that becomes R linear. So this is of course f of P times Rp of V xp comma yp. So that is just f of P times Ap. Okay. Alright, so now what is the Ricci curvature of xy at the point P? Well, that's Ricci curvature of fx comma y at the point P. Well, that's simply the trace of what I have defined to be the BP operator. But because the BP operator is f of P times Ap, and if you have an endomorphism, you multiply by a scalar and take the trace, that is the same as the trace of the original thing multiplied by this scalar, right. So this is equal to f of P times the trace of Ap, but the trace of Ap is simply the Ricci curvature of xy at P. So we have shown what we had claimed in the first part for all P. This happens for all P. So Ricci of fx comma y is equal to f times Ricci of x comma y. So similarly, one can prove part 2, okay, or one can first prove the symmetry and then by symmetry part 2 will also follow. Anyway, let us now prove the symmetry. The fact that Ricci is a symmetric tensor. So now let A xp yp be as before. So remember this endomorphism was precisely R applied to V comma xp applied to yp. Okay, and the Ricci is basically just the trace of this endomorphism. So my claim is that if you look at the adjoint of this operator with respect to the inner product on the tangent space given by the Riemannian metric, then this is simply A of yp comma xp. Okay. So what is the proof of this? I basically just have to calculate what this is, right. Okay, so by definition this is just Rp of V comma xp acting on yp comma w. But then that is precisely the definition of the Riemann curvature tensor acting on V comma xp comma yp comma w. Okay, but now I do the following. I interchange, I use the symmetry to say that this is equal to w comma yp comma xp, which is precisely so if you now I want to use the skew symmetry twice to interchange these two and interchange these two. So that is the same as oh sorry, I got ahead of myself. Right, so this is the same as ypw times V times xp, but then I exchange these two, incur a negative sign, but I also exchange these two. So the two negative signs cancel and I get Rm applied to W, Yp, Xp, V. So then by the same token as above, this is precisely A of Yp comma Xp applied to W inner product with V. Okay. But then because the inner product is symmetric, this is the same as this. Right. So I basically get that A of Xp Yp acting on V inner product with W is the same as the inner product of V with A Yp Xp acting on W. So then by the definition of the adjoint, this means that the adjoint of this is precisely A Yp Xp. Okay, but now I apply this little linear algebra fact. So this implies that the trace of this implies the following, that if you take Ricci of y comma x, then that's the trace of this operator A Yp Xp at this point P. But by our little linear algebra fact, this is going to be the same as the trace of Xp Yp, which is the Ricci curvature of x comma y. Okay. So this proves the symmetry. Okay, so so maybe let me make a remark and then end with right. So let me make a remark and then maybe one can end this this lecture. So the remark is a sort of naive definition would be to instead consider the trace of this operator V going to R of x comma y applied to V. Okay. But unfortunately, because the curvature endomorphism is skew symmetric in these two variables, this would have implied that so skew symmetry of R of xy implies that the trace of this operator is actually identically 0, right. So so the skew symmetry actually implies that if you had defined the Ricci curvature in this way, the trace would have been 0 and you would not get something interesting. In fact, you can try to trace the Ricci curvature in multiple ways. It turns out that up to a sign, whenever you get something non-zero, it actually agrees with our Ricci curvature up to a sign. Okay, so this is essentially a sort of unique way of defining the Ricci curvature. Okay, so maybe I'll stop here. In the next lecture, we will talk a bit more about the Ricci curvature, and I will define a further trace called the scalar curvature. After this, we will take a couple of lectures to talk about hypersurfaces inside Rn, and we will see how to calculate curvature tensors of those hypersurfaces. And then we will move on. So that will finish the first part of the course, namely connections and curvature. Then we will move on to the metric part of the course, namely talk about geodesics and distance function and so on. Okay, so all right, so that's it for now. Thank you for your attention, and I will see you in the next lecture. Thanks.